Today we are going to take another example, which is the example of connecting rods, how to choose materials for connecting rod for high performance engines. So, this is a very practical problem, as you can see here, that these are the typical connecting rods, and the choice of material for such things for high performance engines is highly critical. So, what is the problem that is there for us? A connecting rod is an engine component that transfers motion from the piston to the crankshaft. So, essentially, as the piston is giving a reciprocating motion, that it is putting that force to the crankshaft, so that the crankshaft can actually go from reciprocating to rotating motion. So, it is the other way round of a crank slide mechanism. That means the sliding is coming from the piston and the crank is in this case getting rotated by the connecting rod, the force that is transferred by the connecting rod. So, the function here is that it is a connecting rod, it has to work, that means it has to transmit force from one end to the other, and objective is it has to minimize the mass, okay, it has to be as light as possible. Constraints will be that first of all the length is specified, we cannot arbitrarily choose the length, okay. So, this from center to center length will be specified, okay, and it must not fail by buckling under given force, because as you can see that the connecting rod is going to get a compressive kind of a load. So, it must not fail by buckling under the given force, that is one, and also because this F is repetitive in nature. So, basically as the engine is getting fired, so in the ignition cycle, so the F is going to vary in terms of a maximum and minimum force, F is going to vary. So, that is why in this case the fatigue we have to bring it into consideration. So, it must not fail by fatigue. So, must not fail by buckling, must not fail by fatigue. What will be the free variable for us? The free variable is the cross sectional area of this part of the connecting rod. Now, you may see that the actual connecting rod has couple of additional things. For example, it is not exactly uniform, okay, and secondly it may also happen that certain masses are scooped out from the system. Now, these are the two strategies that are taken. One is in terms of the natural frequency to control that. So, I will not talk about it today, but the resonating frequency is also of concern, and hence if you reduce the mass, what you can do is that the natural frequency of the system, which is square root of k by m, and as you reduce the mass the omega goes up. So, this fellow would not resonate. So, that is one of the strategy that they take. The other point is that depending on the piston part and the the crank part, so the sizes will be different here and here, and as a result there will be a kind of a gradient in the connecting rod. But again, for today's analysis we are simplifying these factors and we are simply considering buckling load and fatigue load and uniform cross section for today's analysis. Now, let us go to the board and try to first find out that what is the performance index, material performance index, then we will come back to the discussion here. So, we are first assuming that the shaft has a rectangular section. So, let us first try to draw the connecting rod approximately here for our analysis. This is one part, and then we have, this is the simplified the drawing of the connecting rod, okay. It is the thickness here or the width here W, which is of concern for us. It's getting the force F. In fact, if you look at the other way around, we look somewhat like this. So you are going to have a block like this, right? And then going to have blocks like this. Okay, and we are going to have slots here. That's the solid part of the material. Right, and of this center line to this center line, the distance is L. This is what is the approximate drawing of our connecting rod. Okay. So what is the mass of it? Let us say again, if we neglect the two sides, then the mass of the rod M equals to simply rho A L, and here L is the length of the rod, A is the cross sectional area, and rho is the density of the material. Now we have two constraints in this case. What are the two constraints? Number one is fatigue, and number two is buckling. So let us take up the first constraint, that is the fatigue. Let us take it up. So from the fatigue point of view, F over A has to be less than or equals to sigma E. That means the maximum force, the stress that will be happening on the connecting rod has to be less than the endurance stress. Okay, sigma E is actually called endurance stress. This is a new property. This property is important against fatigue. And as you know that there are various materials, particularly say for example metallic elements, for which if you actually draw a diagram, you would see that with respect to the number of cycles versus the stress, it goes something like this, so that there is a particular stress level sigma E below which if the material remains, and this is the failure line, okay, this is the fatigue failure. So suppose this is what is my number of cycle, okay, and then if the stress level goes beyond this point at this particular fatigue level, okay, something x number of cycles, 10,000, 20,000 or so, the moment stress goes beyond this, the whole thing is going to fail. But if the stress remain below this sigma level, then you will never come across this line. So that is the good part of it, and hence we always try to keep the stress below the endurance stress level. So, for the maximum possibility, I can keep actually that let the force be such that Fa is just equals to sigma E, cannot be more than that. And keep in mind that area here is the free variable, this is the free variable. So, that means I can write this fellow here as area equals to F over sigma E. Okay. So, once I write that, this is what is my second equation. So, let us substitute that in the expression of mass. So, substituting to 1, what we are going to get is that we are going to get m equals to rho F over sigma E times L, right. And then in that case, what is the material property index? Material index Mi shortly is actually rho over sigma E. You can also keep the performance index, which is the reverse of that, that is sigma E over rho. In other words, from the fatigue point of view, if you want to get a particular material, then your sigma E should be as high as possible and density should be as low as possible. That is what should be your choice. So, I can write the Mi here, which we have just find out, that is rho over sigma E. And then let us move to the second constraint, that is the buckling. So, let us erase this part now and let us think of the buckling. Now, from the buckling point of view, let us consider this to be a slender rod with a critical Euler buckling load. Okay, there is something called Euler buckling load. So, it is the two buckling that we will be now interested in. And from the buckling point of view, there is something called Euler buckling load, which is the first critical load when a compressive member, suppose, is subjected to a compressive force, whatever is the boundary condition, it could be pinned, okay, and then it is subjected to and it deflects either this way or this way. Okay, so, that is the first buckling mode. Of course, there can be even higher buckling modes, but as far as our particular application is concerned, the moment this shape reaches, we consider this to be the critical buckling mode for our design, the first mode itself. And for that, we can write the force has to be less than equals to pi square E I over L square. Again, L you know, E is the modulus of elasticity, and I is the area moment of inertia, So, that is something like, if you think of the cross section here, suppose the cross section is actually, this is W and this is B, then area is BW. Of course, there are many applications where B and W are related, like B equals to alpha W, where alpha we call it to be a shape factor. So, area is BW and B is alpha W, we can keep that in mind, and then we can actually write it down again in terms of the W may be fast, we can find out that if we use these expressions in this particular equation, it will come out alpha cube W to the power 4 equals to 12 F L square. Yeah, so I in this case also, let us write it down, 1/12 B W cube. So in fact you can also write it as 1/12 alpha W to the power 4. So thus if you apply all these things together, it will come out as 12 F L square over pi square E. Okay. In fact, if you work it out a little more, keeping in mind that area equals to actually alpha W square. So if you substitute that here, you will get the area from this as 12 FL square divided by pi square E alpha whole to the power square root. That is what will become to your area from this expression. Once I take the equality in this expression, that means F is maximum possibility of F is pi square EI over L square. With that, if I go ahead, I am going to reach this value of area that I will get from this expression. Now what I can do? I know the area now from this buckling load point of view. I can put it back to this equation 1. So if I do that for equation 1, how would it look like? Let us just erase this little bit of it and just try to find it out, that how will it look like. So if I apply this, applying the expression of A into equation 1, we get M. Let us say in the first case the mass is M1, then in this case the mass is, we can call it as M2, and that we can divide it into parts again, 12 F over alpha pi square under square root L square and rho over square root of E. So we have divided our system into 3 different parts. Okay. In this case, this is the functional part, and then of course the constants are also here, and then we have what you call the geometry part, and the last part is the material property index, that is rho over square root of E. That is what is our material property index, Mi. So we can write that from here the material index that we are getting is rho over E to the power half. Okay. So with this in background, now let us go and see that how are we going to tackle the problem. Now that we know the material indices, should I go for rho over sigma E? Should I go for rho over square root of E, or should I try to do something better for this case? If I now consider both of them, so if I summarize it, that we get in one hand rho over sigma E, and our mass expression in the first case is M1 equals to FL times rho over sigma E. In the second case it was rho over square root over E, and the second case gives us the mass which is of this particular expression. So when the rod has to survive both fatigue and buckling, then it has to survive, the mass should be larger of the two masses, right, because if M1 gives smaller mass than M2, then M2 becomes critical for us, because otherwise it is going to fail in buckling, and vice versa. That means if M2 becomes smaller than M1, then M1 becomes critical for us, otherwise it is going to fall in fatigue. So the best solution for us, so that almost both of them gets violated at the single point, is if I equate M1 equals to M2, and if I do that, then I am going to get this particular expression, corresponding to M1 equals to M2, that is the force part of it, okay. Cc, that is the coupling constant, okay. Now in the coupling constant, if you look at it, that F by L square would become a very critical term in the coupling constant, which is the structural loading coefficient, and that actually comes from the pressure in the piston. So we can denote it in terms of MPas, and then if you look at it, that we can actually draw several lines for, suppose F by L square equals to 5 MPa, which is a high pressure line, F by L square equals to 0.05 MPa, we can do it. And now the plot is such that for us, instead of working on each individual plot, we are now plotting M1 against M2, okay. So M1 and M2 are coming into picture now, the material property indices directly. So that means M1 equals to some constant times the M2, and that constant for two values of F by L square are plotted, considering alpha equals to 0.8. Now then, when in this coupling line, when you are towards the lower border, you can see that beryllium and its alloys, this part actually is coming out as the best choice for all values of Cc within this high pressure to the low pressure range, because you are satisfying M1 and M2 both. But when F by L square is large, suppose something like 5 MPa, then the best choice is somewhere close to this line, that is the titanium alloy, Ti6Al4V, V is the vanadium. And when the pressure is low, and you may also consider the magnesium alloys here. Of course, you have to keep in mind that if you choose the magnesium alloy, you will satisfy M1 more and M2 less. If you choose beryllium, you can satisfy both the conditions 50-50, and corresponding to the case of high pressure, you have only titanium alloy as your choice in this case in terms of the material. So thus we get a very good idea of which material to choose corresponding to the applications. So thus our conclusion is that magnesium alloys like AZ61 and related alloys, they offer good all around performance. Titanium alloy is the best choice for high pressure value. Beryllium is a good choice, a good trade off, but it is difficult to process and very expensive, and also beryllium has a problem, sometimes it is corrosive also. So we normally try to avoid beryllium. And the other thing is the aluminum alloy, which is cheaper than titanium or magnesium, but it has a lower performance. Let us look back the aluminum alloy's position once more. So as you can see here, that aluminum alloys are somewhere in this region, okay. So they are, for the low pressure values, they are not bad, because some good quality aluminum alloys can indeed satisfy our criteria, but of course aluminum is expensive, but in comparison to titanium or magnesium, they could be cheaper, and their performance is lower performance. Titanium gives you the best performance, at least in terms of the buckling parameter. So this is what is our final conclusion, and we can discuss on some more problems in the next material selection. Thank you.